This is going to be an introduction to entanglement entropy in quantum field theories, in particular
Can
three
you
field theories.
can you
Sorry.
please make it the like whole screen, the whole
Okay.
stuff? Like,
Yeah.
yeah,
Is it okay?
fine. Very good. Yeah, yeah,
Also, I have a slightly logistical question. Maybe
yeah.
I can ask that before the talk starts. So, does this email go out to all students?
Yes, I mean, so I send to the all at CHB. So whoever is in the all at
Okay.
CHB, they get the email.
Okay.
And if anybody does not get, so I would request them just to contact me. I will add them in the CC list so that you can.
Okay. Okay. Thanks.
Should I start? Yeah. Okay.
Yes, yes. Please go ahead.
Yeah. Okay. So first, I'll define entanglement entropy and give some basic properties or general properties of entanglement entropy, in particular the UV behavior of entanglement entropy in free field theories. Second, we will go over some simple quantum mechanical examples like two coupled harmonic oscillators, and we will evaluate the entanglement entropy of this system, and we will generalize this idea to n coupled harmonic oscillators. And since we know that the modes of quantum field theories are nothing but bunch of coupled harmonic oscillators, the results from the n-coupled harmonic oscillators can be used to compute the entanglement entropy for the ground states of scalar and Maxwell fields in 4 spacetime dimensions. So let's start. So entanglement entropy is emerging as an useful quantity to characterize a quantum system because it essentially captures the degrees of freedom present in the system near about the critical point. In event dimension, it turns out that the universal contribution of entanglement entropy is proportional to the central charge or the degrees of freedom present in the system. By degrees of freedom, I mean the number of scalar, fermionic, or gauge degrees of freedom present in the system. So our goal is to evaluate the entanglement entropy of vacuum or the ground state for free field theories. Here I will discuss the scalar and Maxwell in 4 dimensions. But before going into that, let's visualize what is going to happen. Consider a one-dimensional spatial spin chain system where we have a spin degrees of freedom, and we imagine cutting the chain at 2 points, and we subdivide the chain in 2 parts, A and B. And essentially it means that we factorize the Hilbert space into 2 Hilbert space, HA times HB. Now one integrates out or traces out the degrees of freedom present in the subsystem B and get a reduced density matrix rho A. Rho A captures the degrees of freedom of the subsystem A. Now we can, once I get rho A, we can compute the von Neumann entropy, which is defined as the entanglement entropy. So entanglement entropy of the subsystem A turns out to be minus trace of rho A log rho A. So this is the overall picture for the 1D system. Now let me define it formally. So suppose we have a quantum mechanical system which is described by a wave function psi, and in the following way, psi as a CAB AB, where AB denotes the complete set of commutating observables. And this means that we have already factorized the Hilbert space HA into HA times HB. Now, given a state of the following form, one can compute the density matrix by taking psi and its complex conjugate, psi star, which has the following form. Now, given the density matrix, one can trace out or integrate out the degrees of freedom of the Hilbert space B and get a reduced density matrix rho A. So here, here we put B equals to B prime and sum it over B. So we get a reduced density matrix rho A, which is sum over B, CAB, C star A prime B. So we put B equals to B prime and sum it over B. Now, once I get the reduced density matrix, one can compute the von Neumann entropy of the corresponding reduced density matrix and get entanglement entropy, which is minus trace of rho a log rho a. Now it turns out that for a pure state, trace of rho a to the power n is same as trace of rho b to the power n, and hence for a pure state, entanglement entropy for a subsystem A is same as the entanglement entropy for the subsystem B. Essentially, it means that integrating out the degrees of freedom present in the subsystem A is same as integrating out the degrees of freedom present in the subsystem B. Now, we would like to visualize what it means by SA is equal to SB for a pure state. Consider we have a 1 plus 2 space-time dimensions. Now, at a constant time slice, we'll have a two-dimensional spatial region. Now you subdivide this into two parts, A and B, and you claim that for a pure state, SA is same as SB. This means that entanglement entropy should be associated with a geometrical quantity which is shared by the both A and B subsystems. And this is nothing but the entangling region which subdivides A and B subsystem. And so entanglement entropy is proportional to the area of the entangling surface to the leading order. And this is little counterintuitive because in thermodynamics we have learned that the entropy is an extensive quantity. But here we have already since we are already integrating out the degrees of freedom in one of the subspaces, so the entanglement entropy is not an actually extensive quantity, rather it goes as the area, it follows the area law. And one can imagine that entanglement must happen, the degrees of freedom are highly entangled near about the this entangling region where the A and B subsystems are subdivided. And actually entanglement entropy diverges when the UV cutoff of the system, UV cutoff of the theory, epsilon goes to zero limit. So let me show the behavior, the UV behavior of the entanglement entropy in even and odd dimension. So you can see that entanglement entropy in even dimension follows first the area law, because in 4 dimension you can see that 4 minus 2 is r squared, which is area proportional to area. And in the power series expansion, we have a log term in even dimension, and the coefficient in front of the log term behaves as a universal term, because if you change the epsilon to 5 epsilon or something, if you rescale the theory, the coefficient in front of that doesn't change, which means that the log term actually is universal in even dimension. Similarly, in odd dimension, there is a constant term which does not depend on the UV cutoff of the theory, and this serves as universal term in odd dimension. So the message is the leading order entanglement entropy behaves as an area, but the universal contribution comes in the log term in even dimension, and the constant term gives the universal contribution in odd dimension. Okay. Now let's consider an example which is a spin system, and we have a state, let's say of the following kind: psi with the alpha up down plus beta down up, and this is normalized with the normalization condition alpha squared plus beta squared to be 1. Now, given a state, one can construct the density matrix by taking psi and its complex conjugate. And to obtain the reduced density matrix, one has to trace out one of the degrees of freedom. Here I have traced out the second degrees of freedom, second spin degrees of freedom. So this will click only when the second spins are identical. So you'll get reduced density matrix of the following form where the second spins are identical. And you can see already the reduced density matrix has the diagonal form with the eigenvalue values alpha squared and beta squared. So the entanglement entropy would be minus trace of rho log rho, which is same as minus sum over I lambda I log lambda I, where lambda i's are the eigenvalues of the reduced density matrix. we get entanglement entropy alpha square log alpha square minus beta square log beta square. Now I flip the second spin in this state. I flip the second spin and let's see what happens. Now here I have flipped the second spin and we have the similar normalization condition, and we have again traced out the second spin and get a reduced density matrix. Now the reduced density matrix is not in the diagonal form, and it has, and one can the diagonal terms are like diagonal entries are alpha squared and beta squared, but the off diagonals are alpha beta star and alpha star beta, and the eigenvalues are alpha squared plus beta squared, which is same as 1 because of the normalization condition, and the second eigenvalue is 0. So the entanglement entropy becomes 0 as 1 log 1 plus 0 log 0 is 0. And the reason for the entanglement, for the vanishing entanglement entropy is because one can write the state in the direct product form. So given this state, we can write in the following way. This means that we can write the state in the direct product form, and the state is actually separable. And the lesson is, whenever we get a separable state or the state is written in terms of direct product of two states, the entanglement entropy vanishes. So this simple example illustrates the statement. Okay. Now let me go over any question, comment, doubts, anything.
I'll just ask one slightly more general question. So, but you might be familiar with it. So, if you're computing the Renyi entropy, there's no for A and B, there is no match, right? It's only only for entanglement entropy it matches.
Yeah, actually it matches. I mean the spectrum matches for the trace of rho A to the power n. Rho A to the power n and rho B to the power n for a PO state. The spectrum entirely matches.
I see.
So the Renyi case also should match.
The density matrix doesn't match, but obviously because it's two different systems, subsystems, but all the eigenstates of the density matrix are the same.
Yeah, correct.
Eigenvalues of the density matrix.
Eigenvalues. Yeah.
Yeah. Okay, thanks.
Yeah. Okay. So let me start by another example, which is two coupled harmonic oscillators. And it has a Hamiltonian of the following form, and where K0 is the natural spring constant of the two harmonic oscillators, and they are coupled by another spring constant K1. And one can go to the normal mode coordinates, and x plus x minus are the normal mode coordinate system, and in that normal mode coordinate system, the Hamiltonian decouples into two independent harmonic oscillators. As you can see, it behaves as two independent harmonic oscillators. And since we are interested only in evaluating the ground state entanglement entropy, so if we get the ground state wave function and get the reduced density matrix out of it, our job is done. So since the harmonic oscillators are decoupled in the normal mode coordinate system, one can write the ground state wave function in just a product of ground state in two normal mode coordinates, x plus and x minus. And as I have stated earlier in examples, that whenever we can write the state in terms of two direct product states, there is no entanglement. So in the normal mode coordinate system, when you have a two product of psi of x plus and psi of x minus, it turns out that there is no entanglement. But one can always go back to the original coordinate system we have, which is x1, x2 system, and write the wave function or the ground state wave function in the following way. But there will be an entanglement in the ground state wave function in the x1, x2 coordinate system. As you can see, it is not a product of psi of x1 and times psi of x2, because there is a coupling from x1, x2. There is a cross term which is x1 and x2. So we have the ground state of the following kind. Now we have to just get a density matrix by taking psi star psi and integrate out one of the oscillators. Here I have chosen the first one. So you take psi star and put x1 equals to x1 prime and integrate over x1. And since it has a simple Gaussian form, this integral can be done easily, and the reduced density matrix has the following form in x2 x2 prime, where gamma and beta are the functions of normal mode frequencies. And here you can see that beta is less than gamma. So this is our the reduced density matrix after integrating out the first oscillator. Now our job is to first find out the eigenvalues or the spectrum of the reduced density matrix rho A. As you can notice that rho A is simple Gaussian in nature. So natural guess would be that if we have a Gaussian or a polynomial multiplied with a Gaussian, then integrating over that coordinate will get back to Gaussian, will give us again a Gaussian. So suppose we have a Gaussian rho A x prime, and if you have another Gaussian, and if you integrate over x prime, you will get back Gaussian. This will satisfy as a eigenvalue equation. And it was rightly guessed by Srednicki, and it turns out that the function, the eigenfunction, is a Hermite polynomial multiplied with a Gaussian, where alpha of the following kind, where alpha is a function of so this is this to the power half. This is alpha is a function of the normal mode frequencies. So we have got the eigenfunction, and one can get the eigenvalues by substituting it back to the original eigenvalue equation, and it turns out to be zeta to the power n 1 minus zeta, where zeta is also a function of the normal mode frequency beta over gamma. So you remember that beta and gamma were the function of the normal mode frequencies, and beta over gamma is less than 1. As you can see that beta is less than gamma, so beta over gamma is less than 1. Since beta over gamma is less than 1 or zeta is less than 1, one can actually sum this zeta to the power n 1 minus zeta, because this turns out to be a simple geometric sum, this infinite sum, and this summation can be done easily. It is like sum over x to the power n, where x is less than 1, so it gives 1 by 1 over x, and the next one is n x to the power n. By simply differentiating one of the 1 over 1 by x, you get the following expression. So this is the expression for the entanglement entropy for the two coupled harmonic oscillators.
So this zeta or psi, that thing is you write it as beta or gamma, but explicit expressions are known, right?
So sorry, which one?
You write zeta as beta or gamma approximately, but its explicit expressions are, I guess, known. That's the point.
Yeah,
right?
yeah. So exactly, it is beta over gamma plus alpha, where alpha is that omega plus over. I just wanted to focus on zeta, that summation. Yeah. The exact expressions are known. Correct. Yeah. So this is the entanglement entropy for the two coupled harmonic oscillators. Now we would like to generalize this. So before generalizing that one, so let me consider the physical origin. Let me discuss the physical origin of the entanglement here. Now consider the weak coupling limit, where the coupling constant K1, which couples to harmonic oscillator, is much smaller than the original spring constant of the harmonic oscillators. So K1 over K0 is much less than 1, and in that case gamma is a function of omega plus and omega minus, and omega plus is square root over K0. Omega plus is square root over K0, and omega minus is K0 plus 2K1 to the power half. And when when K1 is much smaller than K0, omega plus and omega minus both behaves as a square root of K0. So gamma is also linear, also goes as K0 to the power half. But beta, where there is a relative sign between two terms, omega plus, omega minus, and there is a minus omega plus, omega minus, and one has to expand this in power series, and we'll get that beta in the leading order behaves like K1 squared over K0 to the power 3 by 2. So this implies that zeta, which is beta over gamma plus alpha, which goes as K1 by K0 to the power whole squared. So beta over gamma goes as K1 over K0 to the whole squared. Now, when k1 over k0 is much less than 1, or it approaches to 0 in the weak coupling limit, the zeta also approaches to 0, and hence entanglement entropy also approaches to 0. So the source of the entanglement actually comes from the coupling in between two harmonic oscillators. The source of entanglement actually comes from the coupling constant of the two harmonic oscillators. So this illustrates where the physical origin of the entanglement come. So, okay. Any more questions here? Okay. So then let me generalize this to n-coupled harmonic oscillators. And the reason I'm doing this because we know that modes of the quantum fields are nothing but bunch of coupled harmonic oscillators. So we can generalize or we can use the result what we get from here. So suppose we have a n-coupled harmonic oscillators where with the Hamiltonian of the following form, where Kij is a real symmetric matrix, and the normalized ground state can be found easily because this behaves again by going into the normal mode coordinate system where we have decoupled n-coupled oscillators and getting back to the original coordinate system x1 to xn, and we'll get a Gaussian of the following form, where omega is a function of the K symmetric matrix K, because in the previous example we have seen that omega plus and omega minus were square root of K0. So here that capital Omega matrix is also the square root of the matrix K. So omega squared is K, and as we have got the ground state wave function, we can evaluate the ground state entanglement entropy of the n-coupled harmonic oscillators. So once I get the wave function, now we can get the density matrix by taking psi and psi star, and rho is a function of x prime becomes psi star becomes multiplication of the two Gaussian, where now omega we write in a slightly different form. So we write it in a block in terms of blocks, where the A matrix has an index matrix index A, small a and small b, where small a and small b runs over first n oscillators, and I and j runs over the rest. So suppose we have a capital N number of oscillators, and we first separate small n by small n oscillators, small n oscillators, so that this A matrix turns out to be small n by small n matrix, and C becomes capital N minus small n times capital N minus small n matrix. And this makes our job easy to integrate out the first n oscillators, or integrating out the capital N minus small n number of oscillators. So we have the omega matrix of the following kind. Now we have the density matrix. Now we have to integrate out the capital N minus small n number of oscillators. So now we integrate out the oscillators from n plus 1 to capital N. So we have rho d, so it captures the information about the first small n by small n matrix, small n oscillators. So we integrate out the n plus 1 to capital N number of oscillators, and we get the density matrix of the following form. And you remember from the two coupled harmonic oscillators, we had the similar form of the expression of the reduced density matrix. You can see that gamma over 2 there is a squared x squared plus x prime squared and beta x prime, and we have the similar expression xa times xb, and again x prime a times x prime b, where gamma ab is the real symmetric matrix and the beta ab. Now we have to just diagonalize this reduced density matrix by going into the orthogonal coordinate system and get the reduced density matrix of the following form. So we get, after just diagonalizing the gamma matrix, we get the reduced density matrix in the following form, where initially we in the case of the two harmonic oscillator, you remember we had a gamma beta over gamma here, And in this case, the gamma and beta both are matrices. So the lambda is also a matrix with the form gamma inverse beta. So essentially, we have to have a eigenvalues of this matrix. Instead of having a single number, we will have a eigenvalues of this matrix. Initially, we had a zeta in this case, which was gamma over beta. Now we'll have a zeta I. Those are the eigenvalues of the lambda matrix. And the eigenvalues of the density matrix, reduced density matrix, turns out to be the function of zeta I to the power n times 1 minus zeta I. Initially, in the two coupled harmonic oscillator, we had zeta to the power n times 1 minus zeta. Now we have a n by n matrix. So we have a zeta I to the power n and times 1 minus zeta I. Once we get the eigenvalue of the eigenvalues of the reduced density matrix, one can compute the entanglement entropy for each zeta I. Then one has to sum over i's from 1 to n oscillators. This is the same form as we had in the two coupled harmonic oscillators. Yeah. So this is the generalization of the two coupled harmonic oscillators to n coupled harmonic oscillators, and we will use this result to evaluate scalar and the entanglement entropy for the ground state of scalar and Maxwell fields. Now, so far, any questions here? Okay. So now we are going to evaluate the entanglement entropy for the ground state for a scalar field first. Now we subdivide the at a constant time slice, we subdivide the spatial region by a sphere. So we have a sphere. Inside the sphere, we have a one subsystem, and outside of the sphere, we have another subsystem. So this is the way we divide the subsystem, divide the whole space. So we have a massless free Lagrangian for the scalar, which is d cubed x del mu phi, and one can write it phi in terms of phi dot square, and the gradient in the radial direction, and the gradient in the in the angular direction on the S2. So our idea is we will discretize the system in the radial direction. So at each radial point, one can imagine there is a sphere, and that sphere actually divides the space-time into two. And so yeah, now, and since we are in at a constant time slice, we are in 3D space-time, so we can expand the fields in terms of the spherical harmonic basis. So phi is sum over the sum is over L and M, phi LM, Y LM, and phi LM. These modes are the function of radial and time, and all the angular coordinates are hidden in the Y LM. So phi LM is a function of R and T, and Y LM is a function of theta and phi. So this is the way the modes are expanded, and YLM satisfies this orthogonality condition. Now we have to write this. Sorry, any question?
Just a question, Jyotirpal. Yeah. So is this? I mean, are you considering a scalar field theory on a general manifold, like in the background of some curved manifold?
No, this is not a curved. But I have written in del mu, I mean the covariant way, because I'm going to shift in the polar coordinate system. But this is on a flat space.
I see.
This is on a flat space.
Oh,
but this is completely on a flat space. And the quantize, I mean the discretization has been done by a sphere at each radial points.
Okay.
But this is on a flat space, completely on flat space. Yeah. Okay.
This expansion in spherical harmonics, I mean, is this is there a specific reason that why you are considering expanding in, or is it guided by the fact that because your constant surface are the sphere? I guess that's
yeah. Right? Because that will help us to actually manipulate these angular terms. I mean, so you can do it in other bases, but I think this is helpful. This is helpful in the computation perspective.
Thank you.
Okay. Yeah. So once we have the mode expansion of the fields in terms of the spherical harmonics, we can write down the phi dot grad phi and the grad phi in the angular coordinate in the following way. So phi dot will have a time derivative only on the phi lm, because phi lm is a function of radial and time. Ylm has only the angular dependence. And again, the grad phi on the radial direction will hit on the phi lm, but this differentiation on the angular direction will hit on the ylm. Now let me write down the terms. So phi dot squared. So phi dot squared will be because of the root g dqx becomes r squared dr d omega, and phi dot squared becomes phi dot lm, phi dot l prime m prime, and ylm yl prime m prime. Now one can use the orthogonality condition, which is integral d omega ylm prime. So, and using that orthogonality condition, that first term turns out to be phi dot lm and phi dot l minus m. And the minus m comes because there is e to the power im phi and e to the power minus im phi complements and gets 1. I mean, that cancels that thing. So the first term simplifies to that following mode. Similarly, the second term simplifies to del r phi lm del r phi l minus m. Now the third term, which hits on the ylm, so this partial derivative will hit on the ylm. So after one integration by parts, that del I can be moved here, and this becomes a box. The box of ylm gives the eigenvalue equation, which is L into L plus 1 over r squared. So we get all the three terms, and we combine three terms in the following way, and the Lagrangian has a simple form as given in 29. Once we have the Lagrangian, one can evaluate the canonical conjugate momentum by del L del phi dot, which in this case is r squared phi dot. Once we have pi, phi dot, and Lagrangian, we can have the Hamiltonian. Now our goal is to make it look like a Hamiltonian, which is given in n-coupled harmonic oscillator, because we want to cast this problem into that problem. So we'll transform the fields, rescale the fields in a certain way, so that this Hamiltonian can be casted to that n-coupled harmonic oscillators. So our equal time commutation relation was phi lm pi lm. Yes,
I have a question. So yes. I thought you have evaluated this thing on a constant time slice, right?
Correct.
So why are you taking time derivative? I mean, just confused.
Oh, a constant time slice means I'm subdividing the space-time region into in a spatial region into two, but the time dynamics is always there. I mean, the modes will always have a time, right? These modes will have a time and a spatial dependence, but I have divided the space. I mean, at a constant time slice, you are dividing. I mean, that is the division of the Hilbert space.
Okay.
But the modes will always have a time and spatial dynamics. Yeah. Okay. So our goal was to cast it to the n-coupled harmonic oscillator form. So we had a equal time commutation relation, which is I delta over root g. So root g gives you r squared. Now we rescale the fields phi and pi in such a way that this commutation relation becomes I delta r minus r prime, because in n-coupled harmonic oscillator QP was like I delta LL prime MM prime. So we rescale the fields, and the Hamiltonian, under the rescaling of the fields, the Hamiltonian takes the following form. Here we have dropped one total derivative term, because we have an integral over dr. We can drop one total derivative term, and as you can see, this term already looks like the Hamiltonian of the n-coupled harmonic oscillator, where the coupling actually this is the diagonal term. These two are the diagonal term, and actually coupling comes from the radial derivative on it. So when you discretize this Hamiltonian, it will actually look like the n-coupled harmonic oscillator. So let's see. Now our task is to discretize it carefully. So we put this thing on a lattice with a lattice spacing A, which is essentially the UV cutoff of the theory. And also we have a large spherical box with a size which is proportional to the capital N number of oscillators, that capital N. And we place our entangling surface at a point N plus half A. The reason for the half is, so we first integrate out, I mean, we are going to integrate out the first N modes, first small N modes, and we will have the rest, which is capital N minus small n. So we are putting the spherical surface in between N and N plus 1th point. So we are putting the spherical surface at N plus half A. Now we have to discretize this thing on a lattice. So it becomes pi squared becomes that modes pi squared, and the R is written in terms of j plus half squared, and the coupling is actually coming from that radial derivative. And this is the diagonal term. This is the diagonal term coming from the phi squared. So you can notice that it actually looks like n-coupled harmonic oscillators, where this is basically the momentum modes p squared, and this is basically xi xj times kij, where kij was the potential matrix. And the diagonal entries of the potential matrix has the following form: L into L plus 1 by j squared, because this actually gives the diagonal entries. And there is a cross term which gives you the off diagonal term for j comma j plus 1 entries, because a squared minus 2ab plus b squared, that minus 2ab term gives you the off diagonal entries, I mean j comma j plus 1 entries. And kij is actually a symmetric matrix here. So we are successfully able to map this problem onto a n-coupled harmonic oscillators. Now we will be using the results what we have obtained from the n-coupled oscillators. Okay, yeah. So any questions, comments so far? Okay. Okay. So as we have noticed that our quadratic Hamiltonian has the same form of the Hamiltonian for the n-coupled harmonic oscillators, so we can evaluate the entanglement entropy the way we have evaluated in case of n-coupled harmonic oscillators. But we have a summation over L and M corresponding to YLM. That YLM we have got the expansion, so we have to sum over the YLM. And the M degeneracy on S2 is nothing but 2L plus 1. So the summation over M will give you 2L plus 1, and we have to sum over all the modes for L from 0 to infinity. So the entanglement entropy has this following form, where SL is the log of 1 minus zeta L over 1 minus zeta L log zeta L, and this expression we have already obtained in case of the n-coupled harmonic oscillators. Now the question is, does this sum really converge? So we need to know how what is the L dependence of the SL quantity. If it goes like 1 over L, more than 1 over L squared, the sum really converges, and we can obtain the entanglement entropy in this case. Actually, it turns out that this sum converges, at least in 4 space-time dimensions. But it has a problem in higher dimension, which I will discuss later on. So first, so what happens in the higher values of L? So when L is much greater than capital N, the number of oscillators, one can see that potential matrix is already in the diagonal form. So L into L plus 1 is much greater than J is actually running over from 1 to N. So this term actually dominates over this term, because this goes up to N. So this is already in the diagonal form, and one can obtain the zeta L by perturbing the matrix element with the expansion parameter, which is expansion parameter, which is square root over L into L plus 1, and one can obtain that zeta L is actually going as 1 over L to the power 4th. So zeta L goes as 1 over L to the power 4th, and the degeneracy is 2L plus 1. So this sum actually converges, and one can obtain the entanglement entropy numerically at least. So Yeah, this is the statement that one can actually compute SL for each small n or the system size small n, and you put a cutoff L max and you sum it over, and after that it actually means that SL actually converges. And after
Sorry,
that,
Jyotirmoy, just a
yeah,
question. So while it's, I can see that for large L, while the L equal to infinity limit is good, but L equal to 0 limit, it does not diverge or something. That happens.
L equals to 0 limit.
Can you,
Oh,
please,
L equals to 0 limit has to be treated separately. Yeah, I'll show what, but yeah, that
That
SL,
expression is only for large L.
yeah, that expression is actually true for the large L. Yeah,
okay.
true, correct. Yeah. So yeah, so this is how one can actually numerically evaluate the entanglement entropy. And okay, this is just the derivation for the zeta L. This is one can obtain, I mean, we have the matrix of the Kij symmetric matrix, and you you expand the Kij matrix with the expansion parameter square root L into L plus 1, and collect the A, B, C, the blocks of that omega matrix. And with those ingredients, one can also evaluate the gamma inverse beta, and precisely it turns out to be 1 over L squared times L plus 1 whole squared. For the large L, it goes as 1 over L to the power 4th. So the way Sredniki derived for the area term is the following. So he put that spherical entangling surface at n plus half a, and the total number of oscillators he has chosen was 60, and he varied the system size from 1 to 30, and for the each small n one will get corresponding zeta L, and that zeta L can be used to obtain SL, and one has to sum over SL with the degeneracy factor 2L plus 1. So basically we are having SL, the S after doing the sum, S for the each small n or the system size n. Now you can plot that this function S with respect to and with n, and with precisely n plus half squared, because we are interested in the area term r squared. So you plot S with a n plus half squared and get the slope, and that slope gives 0.30. He found it was 0.30, and that's how we got the area term, the area coefficient 0.30 for the scalar field. But this was not this is not the universal contribution to the entanglement entropy. This is just a leading contribution. So this term will vary if you change the UV cutoff of the theory A. So later on in 2010 onwards, the numerical techniques have been developed, and the logarithmic term was found later on. So later, Lohmeier et al. They have found the logarithmic term. Here I have shown their numerical. I have just reproduced their numerical techniques. So they demand that SL goes as AL plus BL over n to the power 2L plus 2, where n is the total number of oscillators. So you can see if BL is very small compared to AL, one can actually take n goes to infinity limit, which is basically the size of the space-time, and this turns out to be some correction to the entanglement entropy. The major contribution actually comes from the AL. So consider here I have plotted, I have got the numerical data points for the L equals to 1, and I have plotted S L equals to 1 with 1 over n to the power 4. And I fit that thing, and I got A and B in the following numerical values. A is 0.6 and B is of the order of 10 to the power minus 50, which is very small compared to the A. So for a fixed value of small n, I varied the capital N, and I got entanglement, got the S values and corresponding A and B. Since this term is much smaller than this one, we can actually drop this one as a finite size correction, and we will only consider the AL to evaluate the entanglement. This is the idea here. So yeah, as I have mentioned that B is much smaller than A, and we can take n goes to infinity limit, and we will evaluate the entanglement entropy by just doing the summation over the AL with the degeneracy factor 2L plus 1. So now we keep capital N fixed and vary the small n, which is the size of the system.
So
And,
when you do this, you're doing it for some very large Lmax, and it's insensitive to Lmax. Is that the idea?
Yeah. So I mean, ultimate L summation has to be done up to Lmax. Lmax is 1000 in this case.
Yeah, my question is, but it doesn't depend. It's like even if you vary the Lmax cutoff, it doesn't change the answer, I guess.
No, it doesn't. It is only, I mean, the point is that in the large capital N, I mean, we are just trying to drop this term. I mean, this is just insensitive to the L. That's what I'm trying to mean here. Yeah. So, I mean, for a given L, for a given small L, we get what is the dependence of the capital N. And then once I get the AL, then we do the summation. That's this cutoff. I mean, your question was whether this limit depends on that Lmax. Is that the question?
My question was whether the quantity itself depends on Lmax. I'm saying somehow you're putting that Lmax cutoff is kind of like just a numerical thing, right?
Yeah. Because as we know that SL actually drops as a 1 over L to the power 4.
So I'm saying that for the So this is basically okay. Fine. I mean, it's basically just the Lmax is when you evaluate numerically, Lmax is just a parameter that you vary, and ultimately it doesn't depend on it. Is the conclusion? Is my only question.
That's true. Correct. Yeah. Then one fits this S with small n because we are varying the system size, and one can collect one can fit it with the following function. This is the area function, and this is the log function, and the coefficient in front of that, which is independent of A. I mean, it doesn't depend on the UV cutoff of the theory, and it turns out to be this numerical value, which is very near about -1 over 90. And in the same year, by Cassini et al., they have confirmed this number is this number was confirmed through some analytical expression, which was based on evaluating the partition function on a hyperbolic cylinder. So this numerical technique gives us correctly the universal contribution of entanglement entropy for the ground state of scalar field. Now we will go over to the Maxwell field theory in 4 space-time dimension. But the result, what we have obtained already in scalar case, will be used here, which is the logarithmic coefficient is -1 over 90. And it will be shown that after this quantization of the modes, that Maxwell field turns out to be just 2 copies of the real scalar fields. So the 2 copies of the real scalar fields, the result of the 2 copies of the scalar fields will be used, but one has to treat the L equals to 0 mode separately. I mean, it has some non-trivial thing, or it actually gives a non-dynamical contribution. So let's start the Maxwell field, and the result of the 190 will be used here. So for the Maxwell field, we expand the modes in spherical harmonic basis. So we have a A0 with a scalar potential, which is expanded in terms of the scalar harmonics YLM. The radial one are expressed again in the scalar harmonics YLM, but the vector modes on S2 are expressed, I mean, the expanded in terms of the vector spherical harmonics YILM, and this YLM satisfies again the orthogonality condition delta LL prime. And now once we expand that in the spherical harmonic basis, like the way we have computed for the scalar case, we will also have a Lagrangian which consists only the modes of the following A0, AR, and AT. And as we know that Lagrangian of the Maxwell field is already a gauge invariant object, So the longitudinal mode doesn't enter into the action. So we will have only a radial and the transverse mode on S2 and also A0. So we will have a AR, we'll have a AT. AT is the transverse mode on S2 and A0 contribution. But we know that A0 doesn't give a dynamic contribution in the action because we do not have A0 dot in the term in the action. So A0 basically gives a Lagrangian multiplier with a constraint in the system, and the constant can be derived by varying the action with respect to A0. So again, see, by using the similar technique the way I have discussed in the scalar case, we expand the modes and write down the Lagrangian. Once I get the Lagrangian, we can get the corresponding canonical conjugate momentum by varying the Lagrangian with respect to AR. I mean the following. I mean, if I want to get pi r, we'll have to vary a del L del AR dot. We will get canonical conjugate momentum pi r and canonical conjugate momentum corresponding to the transverse mode on S2. Again, we rescale the field so that we want to cast it in the n-coupled harmonic oscillator Hamiltonian. So we have the Hamiltonian. We rescale the field in such a way that the Hamiltonian looks like the n-coupled harmonic oscillator. So this is the form of the Hamiltonian. It still doesn't look like the n-coupled one, but we have to modify it slightly. So we again redefine the field pi tilde and a tilde, and so you can notice that pi and AR, the canonical commutation relation doesn't change because this pi r tilde AR tilde commutation relation remains same because L into L plus 1, this L into L plus 1, this R and this R gets cancelled. So after the rescaling and the redefining of the variables, canonical conjugate momentum and the corresponding field variables, the Hamiltonian for the L not equals to 0 mode turns out to be of the following form. And as you can see, it has the same form as we have got in case of scalar field. Let me show you that thing quickly. Yeah. So we have that pi squared, then del phi del r squared, and L into L plus 1 r squared phi squared. So we have, so we can map that Hamiltonian in the following way. So it has two copies of the scalar field, where one of the copies correspond to the radial direction, and the another one is for the transverse mode on S2. And as you can see, the longitudinal mode doesn't enter because of the gauge invariance. And A0 term drops out because it serves as a Lagrangian multiplier and gives a constraint to the Hamiltonian. So we have two dynamical degrees of freedom corresponding to the radial direction and the transverse direction on S2. So we have got the Hamiltonian for non-zero modes, and now let's consider what happens to Hamiltonian at L equals to 0 mode. So L equals to 0 mode, if you substitute back to the original Lagrangian, you get the Hamiltonian of the following form, which has pi 0 squared and also A0 del r pi 0. And as I have mentioned that A0 doesn't have a true dynamic degrees of freedom because A0 dot doesn't appear in the action. So A0 serves as a Lagrangian multiplier, and if you vary the action with respect to A0, it constrains the Hamiltonian. And the constraint equation in this case, del H del A0 is basically del r pi r0 is equal to 0. So if you substitute this constraint again to the Hamiltonian, we are left with only this term. So for L equals to 0 mode, the Hamiltonian has the following form, which has only this term pi 0 squared. And you might have noticed that the entanglement entropy actually comes from the potential matrix, which actually couples the degrees of freedom in the position basis. I mean Kij, Xi, Xj. Here we have only p squared term. There is no Kij, Xi, Xj, that coupling between the degrees of freedom. So L equals to 0 mode actually doesn't contribute to the entanglement entropy because it doesn't have the potential matrix at all. So we have to subtract the L equals to 0 mode contribution to obtain the entanglement entropy for the Maxwell case. Now we have to treat the L equals to 0 mode separately. Again, we do the numerical technique. So that L equals to 0 mode, here I have varied the small n, the system size in small n, from 5 to 55 and obtain the S0. So I plotted the N5 to 55 and S0 gives this following data points, and I fit it with the following function a plus b logr, because I want the logarithmic coefficient which gives the universal contribution. So the a turns out to be 0.88, and b is 0.166, which is 1/6, near about the 1/6. So the statement is that L equals to 0 mode gives 1/6 of the logarithmic coefficient, and which we have to subtract off because it doesn't contribute to the entanglement entropy. So in the Hamiltonian, we have seen that we have 2 copies of the real scalar field corresponding to the radial direction and the transverse mode on the S2. So we have a 2 into -1/90. That -1/90 comes from the scalar contribution, scalar logarithmic contribution. But we have to also subtract the 1/6 because it doesn't contribute to the entanglement entropy. And we need to subtract this because this 1/90 in the scalar case, it already includes the L equals to 0 mode contribution. So if you want to map this problem to the scalar problem, so you have to subtract the L equals to 0 mode contribution. And the logarithmic coefficient after this subtraction turns out to be -16/45. And this is the logarithmic or the universal contribution of the entanglement entropy of the Maxwell field, which is -16/45. So just to mention one point, that this actually agrees with an independent computation which I've done with Justin, which is based on the evaluation of the partition function, the thermal partition function on ADS 3 times S1, and that was based on the conformal mapping structure. This can be found here, and yeah. So this is the logarithmic coefficient we obtained for the entanglement with the Maxwell field. But there are few possible open direction one can go ahead with. So for this method is very robust and very general, and one can use this to compute entanglement entropy for any quadratic Hamiltonian in general for the free quantum field theories. One of the generalization could be for the spin 1 field in higher dimension, but one has to investigate that how does the zeta L behaves and the corresponding degeneracy, because we want to do that summation L equals to 0 to infinity dl SL. In 4-dimension case, we can see that SL that this SL goes as 1/L to the power 4, so that summation was convergent at that time. But it turns out that in higher dimension, that SL has the similar form, which goes as 1/L to the power 4, but the degeneracy increases in power of L. It goes as something L to the power P, where P is greater or equals to 3. For example, in 6 dimension, the degeneracy goes of the following way. The leading order was L cubed, but zeta L still goes as 1/L to the power 4. So it has 1/L kind of thing, the logarithmic divergence. So this is one of the direction one has not investigated yet. So one can go, we feel some regularization is needed in that direction. Yeah. Okay. Thank you. Any questions?
Yeah, I have a question.
Yeah.
So can you last slide that you had, the conclusions?
Yeah, correct. This
one?
So
doesn't it seem a little bit strange that when you're computing the entanglement entropy of like a local theory, you're finding an answer that diverges? But so there should be some way to interpret that divergence in terms of a ultraviolet thing, right?
Yes. That's my point. It cannot diverge. There are other procedures which evaluates the higher dimensional entanglement entropy, but this method should.
Yeah, so I think if you put in a cutoff A that actually depended on the L, then I think you will be able to regulate it in such a way that you'll be able to get a finite result. because I think the point is in some
A is UV cutoff A.
Yeah. So because your UV cutoff is staying fixed and you have entanglement across various L's, right? I mean, L is so I think it might be one reason why you're seeing something which is a little puzzling, because this answer should be finite in any dimension.
Correct.
Finite. I mean, if you have a discrete cutoff or something like that, it looks like it should be finite, right? I mean, there's no reason for it to be.
Yeah.
Yeah. Just
Yeah.
Yeah, Justin, you were saying something?
Yeah. Yeah, sorry, I'm breaking off actually here. But I mean, this there is other hyperbolic mapping procedure, and there's another procedure called branch sphere. All that gives a coefficient actually. But this direct principle, I mean, this direct simple method, somehow sort of has this divergence. So I think there should be some kind of zeta function regularization one has to do. I mean, that's one of the things one can think of. To extract out the correct convergence. I mean, but we haven't done that actually. But this is an open problem. I mean, it's there in the literature. People mention it in the literature, and it has not been solved actually. This.
But it has a finite answer when you do it from this mapping to the hyperbolic space, right?
Yeah. It has the correct expected answers. Like it agrees with the anomaly coefficient and so on. Yeah. So those things are known. I mean, but somehow this simple like Srednicki or even the Sorkin, I think they all once developed such procedures. So that simple one, how to carry it is not solved yet. I think So. Yeah.
It feels like I think the modes are. I'll have to look at your cap, but it's an interesting. I think it looks like a simple enough thing that I think one can try to.
Yeah. Yeah, right. Yeah, I think it is just some zeta function regularization. You have to, do this with the correct zeta function. Like if you could continue this.
There should be some calculation which reveals why there is a problem in higher dimensions as opposed to lower dimensions, because conceptually it doesn't seem like there's any difference. Right?
Yeah. There's no difference.
Somehow it is. I think the fact that the modes are coupling, the spherical harmonics are also coupling with each other in your diagonalization, right?
Yeah.
I think
right.
That's probably something. Okay, anyway, so but it's an interesting.
Yeah, I mean, we didn't realize this was a problem, and it was. People know it, but people don't say it. Yeah, because there are other methods to evaluate it. I mean, so I think.
Yeah. Thanks.
Yeah. Okay. Yeah. Thank you.
Thanks. Yeah.
Yeah. Okay. If there's not any more question, we'll stop it. Okay. Thanks a lot.
Okay. Bye.
Yeah. Bye.